welcome everyone, by the way. Yeah, this works, thanks. Right, so I'm going to talk a little bit about Spinnaker 2 and the stuff I'm excited on at the moment, which is actually using it for kind of non-cognitive applications. So really kind of journal HPC type problems in a sense, but that HPC is bad at solving at the moment. Okay, so a little bit of group intro, but I won't bore you with it. So I've got about 40 people in Dresden. We're pretty broad, so I've got medical doctors actually in the payroll because we have a line of neural implants. I've got mathematics people, physicists, but of course most of them are circuit engineers. We do have 4 spin-offs at the moment. The reason I'm mostly mentioning that is because Spinnaker 2 has been one heck of a logistics nightmare. In the end, we coordinate about 100 persons for setting up that machine, the chip plus the racks plus the thermal management and everything. We couldn't have done it without all the startups. So there's startups chiming in on the communication architecture, doing foundation IP for using 22 nanometer pretty good. With our Bitcoin mining startup, we learned how to do server racks. So all this kind of stuff basically came together with that system. Yeah. So again, what do? We do chip systems. So yeah, we concentrate. That's why I like the full stack approach as well. We concentrate very much on the overall system on chip. So we do stuff on just about every single thing that you can do on a chip. But for us, it's always not putting the ultimate performance in individual components. It's always about, does it work as the overall system? And yeah, we do this across many orders of magnitude in a sense, especially for Spinnaker 2. That thing has 14 orders of magnitude transistors in there. And there is actually not all of the transistors, of course, but there is transistors in there that are handcrafted. So we really touched that machine from the single transistor and upwards. Yeah, so speaking about Spinnaker 2, first off, what is it? Yeah, it's of course an evolution of Spinnaker 1. So it's ARM-based, it has processors in it, it has dedicated compute cores in it, numerical accelerators for various things like MAC cores for DNNs, neuromorphic accelerators, etc. And it's of course built for kind of sparse problems, sparse dynamic communication at a system level, all the way up to essentially 10 to the 14 parameters. So that's the size system you can actually run there, which again, compare it to the latest GPT models, you're about 10 to the 12. So let's say it's the right order of magnitude to impress people, because usually when I go to a conference and show off neuromorphic stuff, people tell me, yeah, it's those guys with 100 parameters. No, so I'm seriously interested actually at the large scale. So of course, Spinnaker 2 will be going from edge to cloud, the whole continuum. But I think we don't have to hide ourselves. Like neuromorphic is always trying to go for the edge. Actually, the brain is 10 to the 14, 10 to the 15 synapses, right? Brain inspiration works all the way from the edge to the cloud. We don't have to relegate ourselves to the edge. We can show stuff at system scale. Yeah, so it's 10 million processors, 70,000 chips. Yeah, and I would say it's the world's largest real-time AI platform because, yeah, any type of NVIDIA system that you run still relies on regular HPC interconnect at the backbone. So it's never gonna deliver a millisecond timescale at this kind of system size. And Spinnaker 2 is actually designed for that. So up to the 10 to the 14 parameters, you still get this below millisecond response time of the machine. You feed in data at the one end, you basically get out the response, actuator, whatever, at the other end inside the millisecond. Okay, so it's been, of course, designed in the Human Brain Project together with Steve's group in Manchester, Steve Ferber. Our best guess is that it can simulate about 50 billion neurons, 50 trillion synapses in real time. Of course, simple ones, leaky integrated fire plus some conductance-based synapse. So that's pure neuroscience. And of course, same as Spinnaker 1, just orders of magnitude, kind of more performance. It's going to be there for real-time AI, real-time robotic stuff. But as I'm going to show you, we can do plenty of more things with it. Speaking of which, I'm going to make a short discourse still in the AI field before I go to the non-AI stuff, non-cognitive stuff. We've been building up a framework which is at the intersection between DNN and SNN. So that's with some of the ex-grad people that are now in Bochum, and one of them is moving to London, which is essentially going event-based for deep neural networks, for GRU networks. So in this particular example, which is called event-based gated recurrent unit, it's essentially a population of recurrently corrected RNNs, and you treat them as a whole as a neuron. So they basically have a threshold stage. They have kind of a dense internal processing, and then they reach some kind of threshold and they send out a vector of scalars to the next unit. So locally dense, globally sparse processing. Now, why are we doing that? Because we get seriously good performance out of it. So performance in terms of classification accuracy is on par with, of course, this is a small scale example, but it's on par with the latest with data augmentation and whatnot, kind of regular machine learning example. But the tricky part is, if you look at this, this is 600 million MAC operations that this model needs for a single inference. The E group plus data augmentation needs exactly 1/60th of that. So this is kind of where I mean, of course, not going again like high fidelity neuroscience, but if you want to marry the best of both worlds, this is actually our current approach, to go really all the way event-based on machine learning. Simple individual computational units, but going for a high level of dynamic sparsity, and actually a lot of biological mechanisms are going in there. There is stuff on the learning side, there is stuff from Hinton's forward in there, there is stuff from expectation maximization in there. So we're putting together a whole weird conglomerate of mathematics to get both the inference and the learning very much down and have kind of the neuronal effects at the population level, not at the individual kind of machine-based neurons. So again, this is of course a handpicked example that worked very well, but on average you get about a factor 10 improvement compared to regular machine learning in terms of the number of compute and memory access as well that you need for a particular problem. And right now we're scaling this up towards, of course, billion parameter language models and visual transformers, stuff like that. So I expect those to become available. I think we're even going to do a homepage on it, like the OpenAI people are doing it late this summer or autumn, basically. Then people can try it out. Okay, so let's go for the non-cognitive stuff. So what do we have? We've got a machine that has extreme parallelism on very simple operations, microcontroller or even below, or even, I mean, if you go full neuromorphic, yeah, just use neurons and synapses, simple computational units. Machine is good for sparsities, searching for sparse solutions in high-dimensional numerical rooms. And there's a lot of mathematical problems that actually map to that. Then it's, of course, very good at stochastic computation. So one thing I didn't mention is we actually use the natural thermal noise in the clock generators, which are in each individual core and spinnaker, as a high fidelity and very high frequency random source. So we can use it directly for stochastic synapses, for coin flips, Brad's algorithms, stuff like that. And it's, of course, built in a mesh architecture, so it also kind of maps to FEM stuff. So finite element methods. So this is a table I've come up with, very hand wavy, but where we're kind of, I would say, in between high performance computing and what's coming up in quantum computing. Okay, so how do we use it? One kind of example that's fairly mainstream these days is, of course, drug discovery. Now, what we're doing here is not AlphaFold. So we're not predicting 3D structures here. We're using those big databases you get of designer molecules. So that's 10 to the 9, 10 to the 10 possible drug molecules. And we do have human-specific coding receptor networks in a sense. Could be DNN, could be SNN. We're not yet decided on that one. And you basically need to match those against this one here. And you need to do it in hours. Current GPU clusters do that in weeks. And of course, you can't do individualized type of medicine when you take weeks to basically scan which of those molecules would be a treatment for that particular cancer of that particular person, basically. So we need to get that dimensionality down. That's this funnel here, because you can test at most something like 100 molecules in real time in the lab. So that's the game. You really need to get the hours down. And we're doing this with Merck, and we recently started talking to the CTO of BioNTech. Those are the, you might know them with Pfizer, the vaccine guys. Now, how are we faster than GPUs? What's the advantage of Spinnaker 2 in this context? First of all, we need to extract. So again, we're not trying to predict molecule shapes. We actually want to extract relevant information from the molecule shapes to match them against the receptors. So we need this marker extraction. That's actually fairly sparse markers, so that fits. And it doesn't fit to a GPU because it's fairly heterogeneous and it's regular C code. So this marker extraction just runs in parallel on Spinnaker 2 on the microcontrollers, basically on the ARM cores. Then the next one is matching that. And this matching, again, because the markers are sparse, basically running them across this SNN, kind of convolutional network, has a high level of dynamic sparsity. So again, runs a lot better on Spinnaker 2. And step 3, there is a kind of coarse sparsity you can lay on top, because once you have figured out that a particular molecule doesn't fit to a particular receptor type, you can rule out whole families of molecules. So there is on 2 or 3 different abstraction levels, there's additional sparsity you can bring in there. And the upshot is that we're very confident we get something like factor 20 to 100 speed up compared to GPU. So that basically gets us down to this hour time scale for scanning the stuff. And right now we've got this implemented on single Spinnaker 2 boards. Yeah. Here's another one, totally different area. Semi-prime factorization. So the usual stuff, you've got a large number that's composed basically of 2 primes, and you want to factorize it. So yeah, what you get for encryption. There's a neat paper by Vignola, factoring integers with a brain-inspired computer. What do? They take the regular number field sieve that's running on ordinary HPC, and they basically invert space and time, which helps in this case because the original space axis is very much broader than the original time axis in HPC. So you can actually parallelize a lot more if you invert it, and you can subdivide that even more. So basically they come up with a network that's very broad, that's very locally dense basically, but then when you put those different, I mean, I won't go into the details here. You can spend a lot of time just thinking about the mechanics here, but it actually goes very sparse when you try to get those kind of candidates that you need to build up this factorization together in this spiky network. So you've got tonic spiking neurons here. They have local dense processing. They try to pick up initial patterns. And then when you get the patterns together, it gets very sparse. So that actually also maps very well to neuromorphic hardware. And one thing we're trying to also put in there is a bit of stochasticity to improve even on that algorithm. So yeah, let's see. So personal goal is, again, we get this down to complexity of days to factorize 800-bit factors. So just for comparison, people on HPC do this at the moment in a month. So that's some serious time advantage. Okay, something else again, quantum. We've teamed up with IQM, which is this large German-Finnish quantum computing startup, to basically do hybrid Monte Carlo sampling. So there's nice theory papers that basically say at the current NISQ scale, so these kind of noisy intermediate scale quantum computers you get at the moment, they should be good at doing Monte Carlo sampling for physics of finite type problems, but they are still too small to represent the problem completely on their own. So you couple them up with conventional computing, which does the explicit Monte Carlo sampling. You've got an implicit model basically running on the quantum computer, and you run both of them in a real-time loop to adjust the sampling in the outside model via the inside, via the quantum model. So again, Spinnaker with its stochastic nature is very good at actually Monte Carlo sampling. So they're basically very keen on kind of using Spinnaker to build up this framework here. So again, we're not inventing the wheel here. This is theory that's already out there since about 7-8 years, but we're using a machine that fits way better to this outside Monte Carlo sampling than classical computing. So that definitely gives us an advantage there. Another fun thing that's also with IQM, they want a digital twin of a quantum computing system because their game is to actually custom design quantum computers. So they want a machine that simulates quantum. Of course, you can do that on GPUs. You build up this whole superposition matrix of probabilities, but it takes a huge amount of memory. And there is a method that's called decision diagrams, which actually gets the memory requirement way down, orders of magnitude. So you can actually do very large scale systems. So upwards of 150 qubits simulated in real time. The thing is, you can't really parallelize it so far. Now, what we've solved together with the guys who invented this decision diagram method is now we do parallelization. We basically cut the quantum circuits apart in many, many sub-instances. And then we arrive at these decision trees, basically, where you do kind of a Monte Carlo transversal of the tree, but each subtree is only a sub-part of that algorithm, while the other qubits that govern the other parts of the algorithm are basically set to certain static value. And that essentially gives you a huge number of parallel sub-circuits, which you then, again, via sparse communication, the results of the sampling you have to set together to the overall quantum circuit again. So again, sparse communication, stochasticity, highly parallel computing of simple stuff. That's where Spinnaker shines. So yes. Yeah. And yeah, this is the one, of course, this is a Loihi example. So optimization algorithms. We're also very keen on looking at Spinnaker too. So Brad and co-workers have already shown you this, their take on it. I won't bore you with this stuff, but this is of course something we will also try out on Spinnaker as well. And either the neuromorphic type stuff, so this is this Roman squares problem that's running on Loihi, or we're even looking at stuff like distributed kind of island-based genetic algorithms or cut and branch algorithms that also fit to the Spinnaker architecture and give you basically advantages for industrial scale process optimization. So just fun fact, this is a couple of us visiting Saarstahl. So that's a big metalworking business about a month back in Germany. And they're very keen on using Spinnaker 2 to basically essentially shave 10–15% off their throughput in the metal presses by doing really online, basically second scale optimization of their factory scheduling. Okay, so that's a software stack because people have been asking me about it. We transfer a lot of stuff over from Spinnaker 1, of course. So a lot of this meta level middleware in between here gets transferred over, gets updated for Spinnaker 2. And then, of course, we transfer over the stuff that's like pi and n interfaces, for example. So the spiking stuff. We will definitely, of course, connect to the deep learning framework. So that's on a single chip level, that's already working. And for this generic computation, there will be wrappers for stuff like the skip package for this numerical optimization, for Qiskit, and for CUDA parallelization. So you can basically plug into the machine also for these kind of HPC type problems, programming type problems that are not really neuromorphic, but happen to fit to the architecture of the machine. Yeah, and just as an outlook. So again, current state of Spinnaker 2 is we had it on Telluride last year. We'll have it on Telluride again this year. 48 node server level boards will be available this summer. And basically the full scale machine in Dresden end of this year. But of course, things won't stop there, right? So we've had 2015, we've had Spinnaker 1, 2023. Now Spinnaker 2 is deployed. About a factor 50x scaling compared to Spinnaker 1. And come on. And the early years, of course, we designed Spinnaker 3, right? So actually this summer, we will start a grant, fairly large one, to get started on Spinnaker 3 design work. And again, the idea is, of course, technology scaling, like whatever we can basically afford, 100x capacity scaling, going even more kind of event-based sparse, because Steve's group has been thinking Spinnaker 1 very much from the system level. My group is coming more from the bottom up, from the multiprocessor system level. So Spinnaker 2 has been designed very much more than Spinnaker 1 on a chip level, but we didn't really connect all the way to the system architecture. So Spinnaker 3 will be more of, again, full stack, but seriously full stack, all the way up to the big compute machine. And basically, yeah, event-based general purpose compute. So this will be an HPC machine, again, for sparse, event-based, extremely parallel asynchronous problems. And one of the outlooks would be really a platform for AGI, because we don't yet know what the algorithms for AGI are, right? So GPUs might play a role in there if you want to have an AGI, artificial general intelligence, but I think something like Spinnaker 3 could also come in nicely there. Come on. Guys? Ah, yeah, thanks. Okay, so that's the end of my talk. That's my group in Dresden. Could you advance it? Thanks. Then there's, of course, Steve's group in Manchester involved. Plus, as I said earlier, quite a bit of our startups. Next one. And yeah, as I said, 5 million core machine in Dresden, available end of this year. You can connect with us, lots of workshops. And of course, Hector is here, who is co-CEO of Spin Cloud Systems. So we commercialize the machine as well. And yeah, Spinnaker 2 definitely won't be a single setup system, basically. So we will, of course, distribute the individual chips like Spinnaker 1, but we're in talks, of course, with Sandia, with Oak Ridge, with Johns Hopkins, various places, lots of German and European initiatives. So at the rack level, at the large machine level, we will basically distribute Spinnaker 2 across the globe as well. So I'm guessing it will be a pretty, well, yeah, Durchdringung is the German word that comes. So it won't be this kind of very closeted machine that's just existing once on the planet. We will really have an impact there, hopefully. So let's make this happen. Thanks.